Hello. Okay. I think we have somewhat noisy audio, but at least there is some audio. Sorry about that, as I had it all set up last time, and then for some reason it doesn't work. um, so, okay. So all the verbal explanation was totally missing. So what this is a live coding exercise to sort of work through how do I write Genesis 2 code. So what am I thinking about, and sort of talking aloud why I'm doing things the way I'm doing them, what the result is, and sort of working through my thoughts on the design process. For this one, we're going to be working on a rasterizer. We're going to be working on an algorithm that Kayvon Fatahelian came up with for doing micropolygon rasterization that I turned into hardware a long time ago. So we're going to rebuild it just for fun. And the idea is that as I'm walking through, if there are questions, you can feel free to ask, or just sit and listen and see what happens. I assume we've lost most people because we started a little late, and then it was just a strange window with text in it. So unfortunately, I haven't quite gotten the sound of typing all the way out. So the rasterizer is kind of broken up into three parts. And the problem that a rasterizer is solving is that it's asking for a given triangle, which pixels on the screen does it cover? So this is how real-time rendering systems work. They take triangles, and then based on the color of the triangle, that's what gets colored on screen. And in this case, we're worried about very small triangles, which are kind of interesting. So you can think of rasterization as having three steps that it needs to do. One is to kind of identify what are reasonable candidates to test. So what are reasonable pixels to think maybe inside or outside the image. I mean, reasonable pixels that are could be inside of the triangle. Iterating over those pixels to test, and then actually testing them. So figuring out are they inside or outside the triangle. So we're going to do. The reason we're starting with this algorithm is it's kind of easy to understand. The very first step or for reasonable candidates would be to look at the vertices of the triangle, draw a bounding box, and then take those, test those. There are more complicated algorithms that work more efficiently for very large triangles, but this algorithm works pretty well for small triangles. All right, and so this is the bounding box unit is what we're working on right here. And the idea is, given n vertices of d dimensions, find the oriented bounding box that covers all of them. And this is effectively find the min and max across each dimension. Cool. So let's see. So we have this S parameter, and we set, so this dimensionality is how many dimensions are there. So we'll start with 2, because most rasterizers work in screen space and are flat. But maybe somebody would want to use this module to do something else. And we'll say that we'll work for 3 vertices, because that's what a triangle is. But if you're curious and open the paper, it turns out that there's a trick where you can do 2 triangles at once, and they share a bounding box. And so maybe 3 would be 4. All right. And then pixel bits. So this is the number of bits anytime we're in screen space that describe the number of pixels. So if we had a really large resolution screen, say that it was 16,000, that might be 14 bits. So we'll leave that at 14 bits. This is a 16K wide image. And then we need subpixel bits. So we will, we'll call that $P, and this is the amount of subpixel precision that we need in the rasterizer. And it turns out that if you dig through the DirectX spec, the number is 8. So that's 8. And then we could put those two numbers together, and that's our bit width for our numbers. So $S plus $P. This parameterization isn't super great because maybe somebody's going to come along later and do something different. So maybe it'd be better to hide the fact that we're doing that and actually just say, hey, what is the bit width here? Because if somebody else was using this for a different application, they may not be interested in having to write out these two parameters to get a number. All right, so, and this is 14 plus 8 is why we did this default. Great. So now we have this guy. So now we need to define the inputs. Sorry, it's super tiny on my screen, so I'm making it bigger for me. So let's see. So I have a for loop that's going to iterate over the verts. So I could build this out as a huge nested array, but that's complicated. One is I'm fairly certain that at some point it's going to break in the synthesis tool. So I'm going to try and leave these as one-dimensional vectors as often as possible. So a vector across things. The other thing is it just makes life easier when you have these sort of flat names. Is that then it just works a little better. It's also sort of helpful for anybody who was wondering how the for loops worked in Genesis 2. So you have this / semicolon, you write for. This my indicates that it's a locally scoped variable. $I equals 0 means I start at 0. $I less than $V, which is the number of vertices. $I plus plus. So this looks like a normal for loop. We're going to close it with these semicolons, and then it's going to loop over the inside. And so one way to think about this is that if there's not a / semicolon, that's just a print statement. So we're going to print this, and then anytime we have these backticks, it resolves to some string. So in this case, it's $BW minus 1. So we said that was $B. But otherwise, everything is the same. And then we're obligated to give back this verts guy. I mean this bbox UR and bbox LL. So we need the lower left coordinate of the bounding box and the upper right coordinate for the bounding box. All right. So we sort of said that the dimensions were separate, so we could just start by looping over the dimensions and sort of go, well, for $I equals 0, $I less than $D, I plus plus. That's probably not great because we used I for vertices before, so we're going to switch this to J's. Loop over dimensions. Great. And then we need to build something to find the min and the max. So let's assume that for now that most of the time it's going to be 3. So let's, just to make forward progress, we'll do some checking. $V equals 3 or a die. you know, we do not yet support non-triangle triangles. Great. So now we can assume that we're always dealing with three vertices. And what we want to do is we just want to compare them so that we can pick the outputs. So let's see. So we're going to need somewhere to put the compare results in. So we're going to have a $C$J. There are, I think, 3 comparisons I can make. So this needs to be a 3-bit thing. Great. And then we can say that zero is equal to, and yeah, we're going to look at verts. So we'll need to do that. And then this is just $J. Better make sure that's in backticks. Yeah, and we'll compare that to verts under 1, $J. And then we'll do a variation on that for 3. So 0, 1, 2. So this will be 1 against 2, and then this will be 2 against 0. Great. So then we need to set up the bounding box for this dimension. So we need to pick an LL and a U. So we'll just build 2 case statements. So we'll have one for picking the lower left, and we will have one for picking the upper right. So let's see, so we can sort of go, well, this is B box under LL, and then we said $J for the dimension, and we have 3 choices, right? We have verts under 0, those are our 3 cases, so we need to come up with the strings that go in front of them. So let's see. So we have 0, 1, and 2. So it's the 0, 0 case if it is 3-bit. So it's, since this is vert 0, so it would be the least if this were true. This one doesn't matter, and then this one has to be 0. So it has to lose the the comparison has to be true, so vert2 has to be bigger than vert0 for vert0 to be the smallest, and then vert0 has to lose the comparison, and then we don't care about that one. So then let's see, 3-bit. And then this guy is 1. So that's going to be the smallest so we don't care about the first case, but it's going to be the smallest if the comparison is false, and then it's going to be the smallest if the comparison is true. There we go. And then this is going to be similarly. Alright, so in order for 2 to be the smallest, it better have lost this comparison, better have won this comparison, and then the first comparison didn't matter. And then this should cover all possible cases. Notice there's kind of a wild card here. The question mark sort of says match anything on the case, so this can be helpful. The one downside of describing it this way is that I think we will have accidentally described some impossible cases, but let's not worry too much about that. So we have the similar thing here. So we're going to copy paste. You are. Great. And so I think if we're lazy, we can just flip all the zeros and ones. But we should go back and double check. So let's see. So comparison 2 would have to be false, yes. And comparison 0 would have to be true, yes. Comparison 1 has to be true, yes. Comparison 0 has to be false, yes. Comparison 2 has to be true, yes. And then comparison 1 has to be false, yes. Good, good. And then this will get us our bounding box unit, right? So let's see if this elaborates the way we're hoping. So the way that the tool works is that top B box needs to exist. That needs to be bounding box. I think it needs to be called my under bounding box. And we're just gonna put this right here. For now, we're gonna hard code this at 3, otherwise we're going to get a Genesis error, and then we should be good. So then we can type make gen module under name equals, we said bbox. So you see a whole bunch of stuff, and then oh no, I made a bunch of errors. Right, so it looks like somewhere I used a bunch of BWs. So I think we said that these were we said it was something like 14 plus 8 is 22. So now we should have a few smaller errors. Let's see. So it's still complaining about bbox.pm. It's complaining about my$d. Cannot locate compile, top, error message, global symbol, $D requires explicit package name. So we're referring to D because we have this dimensions thing. Yeah, so I hurt myself when I deleted that stuff at the beginning, so there were 2 dimensions. You know, the right thing to do is ask for the parameter, and we'll do that in a second. I'm just more worried about the hardware we just wrote. You know, is it elaborating it correctly? All right, so we're getting there. Yeah, okay. Error message, syntax error. At top bbox line 3 near // ask. Yeah, because // is not a comment in Perl. It's sort of wondering what was I trying to do. All right. And then I suspect that I've done the same thing inside of bbox. You know, trying to be too helpful, I've added tons of comments with // there we go. And hopefully, you know, let's see. So if you use strict, you have to scope all your variables. So I never scoped J, so it was kind of mad at me. Yeah, now it finished. All right, so now we can take a peek at what's going on inside of the synthesized design. So Genesis under synth. There should be, I guess it was bbox under unique. So I think there's an error in my test bench. I think this should be a generate under base. Yep, so that worked. All right, so now there should be Genesis under synth. There should be a bbox.view. Great. And then there's tons of stuff. And did my loop unroll correctly? Right, so we have logic 2-0, C0, logic 2-0, C1. It looks like I'm picking the right dimensions. Good. So I'm going to take a quick break. I'll be right back. Sorry, forgot to tell my family I was doing this tonight. All right, so that looked like it came out right. So, you know, now we should, you know, clean this up a little bit to make sure that it's behaving the way we want. So, you know, let's see. Are we happy with the way this looks? And we could come back for this later. If it's not, if we wanted to do 4 instead of 3, that's not that big a deal. And then, you know, maybe for fun we'll come back and do the general case. All right. So now we need to verify this guy. So we got a few responsibilities. So one is we need to ask for the parameters from the module. 2, we need to set up the generic bench. 3, what was the third one? So I need some stimuli for the design. You know, let's just go with random. And then 4, we need a test, and we're gonna go with, you know, sort of the lazy that UR is greater than equal to V, and LL is less than or equal to V. It is that if we do those tests, that should, you know, sort of the opposite way, you know, did we get the selects right? You know, is it actually the bounding box? Alrighty. So it looks like I need to know the parameters way in advance of setting up my signals. So I should probably just move this up here. And then $D, so we need a $V. So let's restore the $V. Is I think it's get param. You know, let's put param RTL. Let's say verif star type get. Yeah, it's get under param. My $V is equal to $. So this is a dereference and a get something. So we're gonna get param. Then we need the param name. So what did we call it in the other module? Its name was vertices. Then we need a $B and we need a $D. We'll go with dimensions. And this was bit width. Great. So now we have parameters set up right. We should make sure to have use strict and all that stuff. Great. So now we have some extra stuff up here to help us stay honest. All right. And then, you know, I always have a little bit of trouble remembering how to set up the generic bench, so I'm going to cheat and look it up in one of my other test benches. So I should have a top under secmol.vp. Yeah. Generate my generic bench. I don't think we need to do a cycle counter. And it looks like we need to instantiate it, so we shouldn't forget to do that. So we should do that down here. We're responsible for some signals going into that, and I believe they are some set of these. So you can kind of see that the pattern I'm kind of doing here is that I'm declaring the modules in advance, pulling out the parameters in advance, and then once I get inside the module, then I'm just sort of looping over these guys. So, you know, that was something else. Probably not going to ask for those. Yeah, I think these are the generic bench signals. You know, we can go peek real quick, trigger start, stop, seed, clock, reset, clock period. Yeah, it looks like most of them are there. So let's see, so we set up the bench. So we need some stimuli for the design. So we just need something that loops over, and what we'll do is we'll do a neg edge of clock, begin, end, and then we had for $j equals 0, $j less than dimensions, $j plus plus, for $I equals 0, $I less than $v, $I plus plus, so now we have some loops that'll get unrolled for initializing our signals. And what we're interested in is this verts input, which is, verts I $j is equal to $random. And then on the off chance that anybody's super clever, we're gonna pad this a little bit. So the issue that we're going to run into is that if somebody is interested in running a test bench that has a bit width that is greater than 32, $random only returns a 32-bit variable. So now it's 128 bits of random. So if we were being good folks here, we might say, well, $b is less than less than equal to 128, or die. Test does not support wide pixel. So nobody will generate the test that it does the wrong thing. If we were super clever and wanted to save ourselves a little bit of performance, because this is going to invoke random 4 times, which might be a simulator hit. We could kind of, if less than 32, if less than 128, all that, but that's kind of silliness. All right, so this more or less defines the driver. Great. So now we have a lazy. We need to do this lazy test to make sure that we're always doing the right thing. So what we're going to do is we're going to look one tick after the positive edge of the clock. And this probably seems a little bit silly. Our design is purely combinatorial. The clock is just coming from the generic bench because it's also used for sequential design, so why use that? The idea is since I have a clock anyway, why not use it to sequence my tests? And then more or less the test is, for the vertices and dimensions, like we just did, am I following the rules? So we can copy those loops again. Make sure to terminate them so we don't get lost. And then we'll write an assertion that the bounding box LL is less than equal to, and then at $J is less than equal to verts I $J. Great. Then we should have the same check for the upper right. This one would be greater than equal to. Great. So now, we're testing that the property should be true. We have some stimuli. We have a property check, and this is, this property is necessary and sufficient for proving that the design works. So formally, if the design did exactly this, if this was always true, the design would always work. And we're going to do kind of a mix of formal and case-based testing to kind of go, well, let's just generate random things, and if it passes the formal test, it's good. So we sort of get the benefit of formal without that. The one thing we're missing is something to say how long we're running. So maybe what we'll do is and we're sort of also responsible for setting up trigger start and trigger stop. So we'll do some basic maintenance. So let's see. So we'll have an initial begin, and maybe we'll make our design a little easier to understand. We'll initialize these guys to 0. Wait until at and it looks like I've done. Oh, it looks like I already have that here. So let's copy paste that in and get us going. All right. So we initialize the triggers. Let's say, don't start collecting activity factors. We're going to wait 100 cycles. We're going to trigger start to start collecting cycles, and then we're going to run for, this is sort of silliness, but let's do 1, 2, 3. We'll do 10,000, and then stop collecting, and then run for another 10 cycles. And this is a combinatorial design, so this isn't going to matter too much, but it's sort of fun. So now we're at the comp stage. Ooh. So single quote versus a backtick. So if you're going to copy paste code, make sure you delete it. Ooh, requires explicit package name. So it looks like in our copy paste code we have some fun locally scoped variables that we forgot to this probably seemed kind of annoying, and this would go away if I turned off the use strict and the use warnings. So the reason to do this is that eventually I will accidentally redefine the my scope, and I really do want an error to pop up. So we get, as far as I can tell, this is a new lint warning that's fun, is unnamed assertion. So let's see, have I started naming assertions somewhere else? In var star. All right, have I given any of the certs names? Pipe it to less. Yeah, so this is the way to name them. So we'll give them some names. So we'll go LL under $I under $J colon UR $I under $J. And I believe what this does is that if you're in the waveform viewer, it'll give that, instead of having an anonymous assertion that triggers, now it's a named assertion that triggers. I would hope that if it actually triggers, it tells you what the name is. So let's see how we're doing on lint and warnings. So let's see. So this all ended up in comp.log, I think. Yeah. So let's see. So we're gonna do grep minus a for. We're gonna look for lint in comp.log. So that was hoping for too much. Great. So it looks like it's still mad at us for these assertions. So it's saying like 86, 87, 98, 99, 100, 101. All right, so let's actually load up Genesis under Verif. And this is top under bbox to see what's going on. All right, so we do have these assertions. I guess it's saying it's a null because I don't do something. So let's see. How do I get rid of these null errors? Null statement, lint. I mean, one thing to do would actually be to get rid of it. So I could mask the lint warning. I suspect what it's looking for is that it's kind of hoping that maybe, I'll do something. So this seems like a tiny deviation. So the reason I'm worried about this is that later on, I'm going to want to run. I'm going to want to run a tool to kind of go, okay, how many lint errors were there? And if there were too many, I'll be worried. All right, so it looks like I still had lints from these. Yeah, so it looks like these are still mad at me. I think there's like $1. There we go. Great. Did this make it happy? Is sort of the thing. So now it's mad that so now I still have null statements, but now it's mad about token is else. So did I need a semicolon there? Because this is technically like a if-else clause. It seems like I'm having more and more that it's sort of going use a pass action block. Uses a pass action block. So maybe what we actually want to do is be really clever. So maybe instead of doing this, what we'll do is we'll keep count. So else error plus plus, else error plus plus, and then we'll do pass plus plus, pass plus plus. So now we need to add these. And then maybe we actually want to look at them when we're done. So final begin end, dollar display. So let's see, we'll do pass %d, fail %d, and we'll do total %d. It gives us the new line for free, so that is pass error and then pass plus error. Great. So now we should get a cool little message at the end with our total cases. And then if I was super clever, maybe I'd pick better names. Ooh, so what was it mad about? Source has a syntax error. Yeah, I forgot the semicolon again. Maybe this will get rid of the error. And the whole reason I'm running this down is this is irksome when you're writing the code and it's you get, man, the lint errors are still there. Oh, a lint pass action block. So somehow I've made this non-sampled variable used. So it was catching that I wasn't initializing these. So wow, okay. So how are we doing on lints? So we still get the null statement. And now we've made it worse. So now we're getting these non-sampled variables used. Interesting. Interesting. Well, I guess there's some mysteries we'll have to let alone for a bit. Maybe running it will tell us what was going on. So we'll quick check for warnings. So it looks like there was a unsupported kernel and one of the command line things doesn't work. All right. So I think this was make run. And then it worked, and then we ran thousands of tests, and they all passed. So good. So we can feel good that the block works. So this is interesting. Genesis under 6th, no condition max in bbox.vp. Unique case statement default, missing it at time 0 nanoseconds. So one way to get rid of this, is to come back to this guy. Right, default. Pass. bbox. $J equals 0. But really what's happening is that there is a case at 0 times, so the very first tick before anything is defined, where for some reason this procedure block is running. Ooh. And hopefully, you guys spotted the copy paste error. If you copy paste but don't change the text, you'll get a multiple driver error. So that means you're trying to write to the same thing twice. All right, so now we got rid of the warnings. And then the synthesis tool should know that it can blow this case away, so that it doesn't need to examine this. But just in case, it's feeling, kind of ornery, we'll make sure that it is resolving to the right thing. So it's a constant of specified bit width. So it has enough zeros. And then so now we need to, so this seems like a relatively good place to stop. So far we have a bounding box. The code for this isn't too complicated. N vertices of d dimensions. It's pretty simple stuff. The thing that we're gonna do next time is probably get the iterator working, or try and figure out how to get rid of these assertion bugs, because I'm kind of irked that writing an assertion somewhere like this works that way. Maybe maybe it needs to be a property. So so I feel like there's a way to get rid of this, and I do it. I've gotten rid of it before. I just need to remember how. I suspect that by transforming these from assertions in an always block to properties, that it'll work a little bit better. One problem is that with properties, there's a little bit of difficulty getting it to control when it executes. You have to be very precise, but that's not too big of a concern. All right. Well, thank you for hanging out. I hope that the 3 or 4 of us following along, we're enjoying it, and I will try and consistently do this sort of Wednesdays at 6, and hopefully next time I actually sign on time. But if not, I'll probably see you in class tomorrow. Have a good one.